Hello, um, welcome to another video recording session, video log of me talking about genetic algorithms, and the date is 2025 March 7th, and today I'll be covering well, this is part of the grid search process. And if we remember correctly, well, you might remember that I talked about different ways of procreating, or different ways of procreation, or parent selection schemes, different parent selection schemes, as a way of carrying out grid searching. So this notebook is just that. In this notebook I'll be going through different procreate functions, and let me see if I'm actually gonna run anything. How many generations do I usually have? 11 seconds. Maybe not. I don't know. I might or might not run things, but that might be on the results that are shown here might be from my laptop, so I don't know that, so I'll just have to check. So we start off exactly the same. I import stuff. I create the void genes, I create the items list, values list, and the constraints list, and the functions as well. I don't use the random gene generator here. I do use the fitness calculator, the constraint calculator, and the selector, and this is what used to be the procreate function. Instead now it's in a function, but that is not in use. Instead we're going to try to select the parents differently, or procreate differently. And now I say procreate differently because at the very first procreate function, or function that I'm going to cover, is I just named it Lonely Island, or what it does is it self-replicates, or rather this function copies the very top performing entity. Again, keep in mind that the word top performing, or the definition of top performing, may change depending on the environment, the conditions, depending on what the problem is. But anyway, as of that moment, this function will just copy the top one and return that. So if you need 39 new entities, if you use this function for 39 times, you'll get the top entity, but copied onto the next generation 39 times. Yeah. I mean, so as a result you'll have 40 copies of the same top entity. Next one, I call it the monopoly elitist. Now what this does is it takes the top entity, and keeps that as one of the parents, and the other parent is chosen from the top 10%. So yeah, so it's chosen from the top 10%, and then they procreate as parents and returns 2 children. Yep. Next one is again also named Monopoly, but this one is called well, this one I dubbed it as the winner takes all, because in this case the top one is still fixed, but for the other parent, you don't the other parent is chosen from the entire pool of entities. So the top entity can go ahead and procreate with the bottom one as well. It's completely random at this point. Next one is called the oligopoly. I said that right? I don't know. Oligopoly. And what this does is, this is different because in this case the top one does not exactly stay fixed. However, the top 10% of all the entities are chosen as elites, but not to be confused with the Monopoly elitists, but the top 10% are pulled together, and then from that group are chosen the 2 parents are chosen from that group. So the top entity doesn't always get to procreate. This is all at random as well, but at least within the top 10% of the entities within that generation, and then returns 2 children, child 1 and child 2. The next one is favoring highs. This is slightly similar, but in this case, what happens here is that after the entities have been lined up in decreasing order, from the entity having the highest summed utility value to the lowest summed utility value, and all of the entities will have weights by which they will be chosen at kind of random, but it's not exactly random. It's not absolutely random, but they'll be chosen according to their weights. However, the weights in this case are computed as something like this. If the population is 500 and the first entity's weight is calculated by dividing it by 1. The second entity's weight is calculated by dividing it by 3. So on and on. So first, second, third, fourth, fifth, sixth, and on and on and on. So 1, 3, 5, 7, 9, 11, 13. You divide that. You divide 500, or the number of the population, by these numbers accordingly, and that's how the weights go. So if it's 500 divided by 1, the first entity will have a weight of 500. The second entity will have a weight of 500 divided by 3, which is, I think, 166.6666. And then the third entity will have a weight that equals 500 divided by 5, which is 100. So that's how it goes. So eventually the entities that have higher summed utility values are very much more likely to be chosen as parents. And this function returns 2 children. But what is important to note is that it doesn't matter in what order the parents are chosen. That goes the same with all the other functions as well. And the next function is it's named proportional, and this is because the weights again for all the entities are summed, are computed by, well, according to how much their individual summed utility value is. So if the summed utility value is, for example, 100,000, let's just keep it simple, 1,000, and the first entity has summed utility value of 500, and which is half, and the rest have, and the next one has 100, which is 10%. So in that case, the first entity will have 500 over 1,000 chance of being chosen as one of the parents, which is 50%. The second entity having 100 divided that by 1,000, which is 0.1 or 10%, therefore has a 10% chance of being chosen as one of the parents, and on and on and on. If an entity has a summed utility value of only 10, that is 10 out of 1,000, which is 1%, so that entity would have 1% chance of being picked as one of the parents. That's how it is. And then this function also returns 2 children, and this one is called less favoring highs. This is exactly the same as this one, favoring highs, but in this case the weights are divided by not 1, 3, 5, 7, 9, 11 odd numbers, but in this case it's divided by 1, 2, 3, 4, 5, 6, 7. So all natural numbers with an interval of 1. So the 10th entity, so the weight of the 10th entity will be population divided by 10. The first entity will be population divided by 1. The last one will be divided by the population, I think. Yeah. Again, returns 2 children. This is kind of interesting. This one's called opposites attract. This is kind of an elaborate scheme to compare genomes, compare entities that are different. And the way this is computed is that if an entity is 1, 0, 0, 1, 0, 0, 1, and another is 1, 0, 0, 0, is that right? Let's just do this. And then the other one is 0, 1, 1, 0. If this is chosen, this one will be the parent, the other parent. So the purpose of this function is to mimic human marriages, or human marriages that kind of happen because the couple feels that the couple of humans feel that they are attractive because they're kind of different, or the opposite, and they complement each other. And that's how it is. And yeah, but in this case, the first parent is chosen at random, and when that is chosen, the other parent is chosen according to this difference, and we go for the max difference, the entity that has the maximum difference from that parent 1, and that will be, which will be called parent 2, and then they procreate and then return 2 children. Birds of feather is exactly the opposite, where a parent is chosen at random, and and the other parent will be chosen by a process where the result will be the entity that has the minimum difference. So exactly the same as opposites attract, but birds of feather is we go for the minimum difference, and then when those two parents are chosen, they procreate and return two children. And then this one is just pure chance, random. So what this does is it just picks two parents at random and then they procreate. It doesn't matter how high or low or medium or median or average, whatever. It doesn't matter what their sum utility value is. It just chooses and then procreates and returns two children. And then the mutate function is still used, and we set the hyperparameter max constraint. The weight threshold is 4000, population size is 500, number of items is 20, so is the genome length. Mutation rate is 0.03 or 3%. Crossover rate, I don't use that. Generations, this changes every time, so that doesn't really matter. And we start the evolution. We first go with Lonely Island, and I ran it for 500 generations, but let's try again. Remember, oh, I didn't run anything. So bad. I'm so dumb. Need to run everything. Run the hyperparameters. Make the genesis the initial population. Commence evolution. For the first one being Lonely Island, where the top entity is replicated. Cool, all done. 10 seconds. And let's see what happened. Remember, the maximum sum utility value possible in this under these conditions is 710. So we did get 710. Wow, how perfect. I mean, for now this looks perfect. It's good enough, or more than good enough, now that I know the answer. But somewhere down the line, I know that this is not always the case, and some adjustments and some concerns have to be dealt with. So that's that. These are the values, and they're kind of high up. I do need to find out or create another notebook to study the distribution of these entities, but I'll do that later. The next one is Monopoly, elitist, where the top one stays and the rest, the other parent is chosen from the top 10%. So there are 10 Procreate functions. And we assess. We struck gold again. We have 710 again. Wow, so good. it's not. This is not the best. But anyway, for now, this is good. This will do. Monopoly, winner takes all, where the top one stays, and the other parent is chosen at random from the rest of the entities, the entire population. Awesome, we have 700. Nice. This is also, seems to be working fine. Oligopoly. This is where the top 10% are the candidates for being the two parents. No entity is fixed as parent one, but anyway. But two entities will be chosen from the top 10%. 705, awesome. Very, very close to 710. Actually, it is the second highest summed utility value, so that's good for now. I assure you, it is not good, but that's for another video. Favoring highs, where the weights at which entities are picked is computed by dividing the number of generations. No, dividing the number of population. Sorry, not generation. Dividing the number of population by 1, 3, 5, 7, 9. Odd numbers. I mean, the numbers that you divide by can change. It could be 1, 5, 10, something like that. But for now, it's odd numbers. That also worked. 705, which is so far. If you remember correctly, we are consistently getting entities that are above 700, which seems fantastic, because previously I've only been getting 680, 690, 695, sometimes 60, 660, 670, so very low compared to these. Proportional is, I've explained it, where the weights are the sum, where the individual weight of an entity is its summed utility value. And this time it seems to have worked fine. 685, because last time the top one was 635, but for but this time I could say that we got lucky. If we try again, it might not give us 685. It might give us something like 650. Yeah, 635. So 680 was very lucky. Less favoring highs. This is where the weights are computed by dividing the population by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And what do we have? 675. So if you look closely, it's the highest is 675, and for the favoring highs, the highest there was 705. So we have a difference of 30 in terms of summed utility value, and it is, if we run it again, this will change, but if we run it again, it is very likely that the top entity is still going to have a lower sum utility value compared to when using favoring highs. It's still 705. Wow. Really? Oh, it actually worked out this time, so that's good. Sometimes it works, sometimes it doesn't, but later, spoiler, the one spoiler that I can share right now is that well, this one, when you use the less favoring highs Procreate function, you tend to get less frequent entities. You tend to get entities that go over 700 less frequently. I think that's the right way to say it. And so, going on to opposites attract, number 8, where one entity is chosen and at random and the other parent is chosen by searching for the entity that is the most different from parent number 1. This one takes quite a long time compared to the other functions, because within the process, within every process, within every loop or iteration, the computation and the ordering of entities according to the summed utility values have to be done, processed, and that takes time. So 630, which is quite low than the other high performing functions, but for now this looks bad, and for now I could say this is bad, but it will have its own use later, I believe. Next one is birds of feather, and before I run this, actually after I run this, I'll say it. Where the entity is chosen, parent 1 is chosen at random, an entity is chosen as parent 1 at random, and the other parent 2, is chosen by searching for the entity that is the most similar or the least different. Yeah, 22 seconds. 6:15. So, not so much. But I believe this will also have its own use later. Pure chance. What else is there to explain? 2 parents at random. 2 entities chosen as parents at random. Completely random. No weights, just equal weights. $6.40. So what I was about to say, and what I'm first, as I'm about to start my rant, is that birds of feather and opposites attract can be used with one of these other functions. For example, I could just use it to use it with Monopoly Elitist, or use it with Lonely Island. These two functions in tandem, where the top entity is fixed, or where one of the elites is chosen, and I could use opposites attract to get the entity that is the least similar and have those procreate, or I could do I could use birds of feather to look for the entity that is the most similar and procreate. Well, that is the end of this notebook, this Jupyter notebook. But I can say that I can say right now that I think that was a saying, not everything that glitters is gold. Because although these top ones, or these functions from 1 to maybe 6, 5 look good, even number 7 looks good, but there are some problems that I have faced as of now, since this notebook was this experiment was done like a few weeks ago, and I have done some more work after this, and I have faced some it's not a problem, it's just a phenomenon, it's just a weird occurrence, and I have dealt with that weird event, or issue, let's just say. It's not a serious issue, but it is an issue nonetheless. And yeah, so I'll be recording that later anyway. So lastly, if you look closely, from number 1 to number 10, you could say that number 1 is the most harsh, and number 10 is the most generous in terms of competitiveness, in terms of competition. This one, for example, when using Lonely Island, only the top one gets to procreate. The rest, they don't matter. Number 2, sorry about that. In number 2, the top one is fixed, but the other parent is chosen from the top 10%. So it gets more lenient as the number grows from 1, 2, 3, 4, and for now we end up with number 10, pure chance, where for now this is the most generous one, because the 2 parents are just chosen at random. There could be more generous ones where I could just I could make additional functions which pick the entities with the lowest summed utility values and have them procreate and see what happens. Yeah, I could do that. So anyway, this is from number 1, most harsh or most competitive, number 10 being the least competitive or most generous in terms of survival, and summed utility value wise. So that's that. Thank you for watching. See you next time. Love you. Peace.